in this video, I will be showing you how we can reason given a certain set of logical expressions in order to make sound and correct inferences and to draw out the right conclusions from those sets of logical expressions. We are doing this after we learn about propositional logic and then predicate logic, so that we will be able to apply inference rules on both propositional and predicate logical formulas. We will learn in this video about propositional logic rules, and then on Thursday we will discuss these rules, and we will conclude the discussion with inference rules for predicate logic formulas, which are simply 4 different rules, but they have to be carefully applied to instantiate and generalize predicate formulas when it comes to quantifiers and variables. So let's start with the general introduction. And let's revisit the Socrates example that has actually 2 premises: all men are mortal, and Socrates is a man. And logically, intuitively, we would like to conclude from these 2 sentences that Socrates is mortal. We are quite close to this to be able to make such conclusions, but we just need to learn about inference rules right now, because until now we learned how to represent such concepts, typically in predicate logic. But we still need to learn about how to draw out conclusions using valid arguments, in other terms, by applying what we call inference rules on these premises in order to conclude this statement. So how do we get the conclusion from the premises? We use inference. Inference is actually the process of driving logical conclusions from premises using what we call inference rules, and which are believed to be valid, sound logical steps that we call actually intermediate arguments. So we have to argue with one sentence after the other by applying the inference rules until we get to the conclusion. So we use arguments in inference, and an argument is actually a sequence of premises and a conclusion where there is a strong correlation between the premises and the conclusion. If premise 1 and the premise 2 and up to premise number n are true, then necessarily the conclusion C must be true. So an argument is valid, an argument holds if and only if this implication is a tautology. Okay, this argument or this implication is always true. It means that just in case these premises are true, then necessarily the conclusion is true. Since it's an implication, the fact that the implication is true does not necessarily mean that the premises are also true. Okay, the fact that the implication is true simply says that just in case those premises are true, then the conclusion must be true too. Okay, so for example, in maybe investigations and forensic science, we may have a rule that says that if a person was on a certain crime scene, then that person is actually a potential committer of that crime. But we still need to check the truth of the premises. Okay, so we need to check the facts to conclude whether that person was really on this crime scene, or not, and whether it was at the same time, etc., etc. So you need to check your premises. So the fact that the implication is true does not necessarily mean that the conclusion is always true. It just means that just in case the premises are true, then necessarily the conclusion is true too. So our goal is to show that if the premises hold, then the conclusion also holds. And we have two types in arguments in logic: arguments in propositional logic that we're going to learn in this video, and arguments in predicate logic that we're going to discuss on Thursday. Let's check the first types of arguments. You will see that these are the essence of inference. Okay, the rules for predicate logics are only 4 rules, and they are straightforward to apply. But we have several different rules or valid arguments in propositional logic, so we need to learn them and to master the way we apply them. So an argument in propositional logic is a sequence of propositions. All but the final propositions are called premises, and the last statement is called the conclusion. An argument is valid if the truth of all its premises implies necessarily the truth of the conclusion. So for example, intuitively, if you have this rule, if you have a current password, then you can log on to the network. And given that you actually have a current password, then we can safely conclude that you can log on onto the network. It's quite similar to the Socrates and mortality of man example. An argument form in propositional logic is a sequence of compounded propositions involving propositional variables, okay? And it's valid if the truth of its premises implies the truth of its conclusion, no matter which particular propositions are substituted for its propositional variables. So the argument would be considered valid just because it respects certain syntactical structures, certain syntactical rules, okay? So for example, the following sequence of propositions is a valid argument form. P implies Q and P. If both are true, then necessarily we should conclude that Q is true too. Okay, and this is a valid argument since P implies a Q. Sorry, since P implies a Q, and P implies Q is a tautology. If you have P implies a Q and you have P, then you have you can conclude Q. Well, this is a tautology, and I can show it to you in a couple of slides. So an argument form with premises P1 up to Pn and a certain conclusion Q is valid if and only if this conjunction implies that conclusion is a tautology. Okay, so if we consider these actually formulas, we can show that this is a tautology. How to show that this is a tautology? Well, you can use truth tables, okay? Or you can use equivalence rules and show that this is equivalent to true all the time. For instance, actually, we can, even when it comes to equivalence rules, you can apply it in several different ways. So for example, we can unfold the inner formula to actually we can unfold this one, so it becomes not this formula here, P implies a Q, and P or Q, okay? So this implication can be unfolded into this form, not A or B. Okay, A implies B, it's not A or B. I'm sorry, guys. Okay, it's not A or B. And then we get the negation inside these parentheses. So we get not P implies a Q or not P, because we are applying the De Morgan's law, or Q, which is equivalent to, so not P implies a Q, it's P and not Q, okay, or not P or Q. Okay, so now we can apply the distribution rule on this one, and you can finally find that it is a tautology. So what would be this one actually? So let's apply it on these two formulas, A and B or C. So let's see this as A and B or C. Okay, so we'll end up having and let's distribute this disjunction over this conjunction here. So we'll have A and so A or C. Okay, so we'll end up having A or C and B or C. Don't you agree? Okay, so A or C is P or not P or Q, and okay, so and B or C, which is not Q or not P or Q. Okay, I remove the parentheses around C because I'm ending up having disjunctions everywhere, and the or operator is associative. Okay, so this one is equivalent to that one, to that conjunction, which is also equivalent to, well, here you have P or P, so it's a tautology, or Q, so it's a tautology, and it's always true. And not Q or Q, it's always true. Okay, true or not P is it's equivalent to true. So now we have true and true, so which is always true. Of course, we could have proceeded in a different way by analyzing the formula A first, and then we could analyze it with Q at the end, but you will get exactly to the same place. Okay, so but do you see, instead of always doing these rewritings whenever you have something of this form, A implies B and A is true, well, this must imply B all the time. Okay, so instead of doing this all the time, why not to give it a name, to give it a rule, so that whenever you have A implies B and you have A, then you can conclude B out of it. And we use this symbol to say that B is a conclusion of these two facts, of this fact and that fact. Okay, well, actually, this is the first inference rule that is called Modus Ponens. So congratulations, you have learned the first inference rule. It's and I have just showed you why it is a valid inference rule. It's a valid inference step just because the premise number one and the premise number two implies the conclusion is a valid tautology. Okay, and we actually, all that you have to do is to learn about more rules so that you can apply them in order to perform inference afterwards. So we can always use the truth table to show that an argument form is valid. So we show that whenever the premises are true, then the conclusion is also true. But this can be very tedious, you know it already, because for 10 different propositional variables, you end up having 1,024 different rows. Okay, so it's not practical. So in general, you will end up having 2 to the power n rows whenever you have n different rows. And this is really tough for when done on paper, and even for machines when we get a large number of propositions, such as 56 propositions or 128 propositions, something like that. Okay, so instead we use a set of relatively simple valid arguments that stems from the equivalence rules and the definition of connectives that we call inference rules. They become our tool set or toolkit to prove to create arguments, valid arguments, and to show that a certain conclusion stems from a set of premises. We use rules of inference as building blocks for more complicated valid argument forms. Okay, and your only way to master them is to keep your slides that will start on the next page number 9. you keep them as a cheat sheet and you solve all the exercises while checking these rules and applying them, etc. Okay. A good practice also is to be able to prove all these inference rules at least once, okay, just to convince yourselves of their truth or of their validity and soundness. And afterwards, you can just use them without proving them, okay? So for example, I have just proved this implication with you. I showed you how to prove it as a tautology. I'm not sure if this is done in the slides here. No, it's not done. You just have a few examples. And since premise one and the premise two implies conclusion is a tautology, since we have shown that this is a tautology, then we can confidently say that given this premise one and that premise two, we can conclude this conclusion at the end. Okay. So this is the Modus Ponens used by ancient philosophers, ancient Greek philosophers. So we are talking about 2,300 years from now. Okay, so it's a very old a way of thinking, of a human thinking, logical entailment and logical inference. You will see that the other um, um, forms of inference are just certain derivatives of this form here. Okay, they just play on the definitions of the connectors and their correlation with the implication. One last word about the modus ponens. I just want you to know that this is the very basic um, idea behind logical inference. So if you consider besides these examples, the example of rain and the cloud. So if you have the rule that says whenever you have rain, you must necessarily have clouds in the sky, and if you look out of your window and you see rain today, then you can confidently say that today there must be clouds in the sky without even looking at the skies. Okay, so um, implications are typically called rules. Okay, and simple propositions that are believed to be true are called facts. Okay, together they build what we call your knowledge base. Okay, so you have your knowledge base or KB in short, and usually from a certain knowledge base, from a certain knowledge on certain rules and certain facts, you can draw out valid conclusions using what we call the inference rules. So this is why, since the beginning in the introduction, I told you that learning about inference rules and how to apply them, it's the most interesting part in these chapters about logic. And you will see how we can use them actually to create valid proofs in mathematics, whether it's a proof by contradiction, a direct proof, a backward proof, or proof by induction, strong induction, etc. So in the next part about proofs, we will be heavily using these inference rules. Let's learn about the second one. The second one actually stems from the equivalence between the contrapositive and the implication. So an implication is logically equivalent to its contrapositive form. So I mean, when you have P implies a Q, well, this is 100% equivalent to not a Q implies not P, okay? Um, so this is why when you have in your knowledge base a certain rule that says that P implies a Q, but you have not a Q. Okay, if you have P, then you can conclude a Q. But if you have not a Q, then necessarily not P must be true. Okay, so how can we conclude this? Well, the modus tollens is just another way of seeing the modus ponens, actually. If you rewrite, it could be called the contrapositive of the modus ponens. Okay, so since P implies Q is 100% equivalent to not Q implies not P, so now we can apply on this new formula, not Q implies not P, as an equivalent premise to P implies Q. We can apply to it and to not Q the normal modus ponens to conclude not P. Okay, but yeah, the name modus tollens, it's really required to allow you to do this step without even rewriting your formula, okay, without using modus ponens and rewriting your formula. You can straight away apply this rule. And when it comes to the intuition of this rule, well, actually, when you have rain implies clouds as a rule, well, actually, when you don't have clouds in the sky, okay, so you could not check the earth to see whether it's wet or not, but just saw the sky and you notice that there are no clouds. It's crystal clear. Then in this case, you can confidently say that it could not rain today. Okay, it cannot rain today. It's impossible. Okay. Good. Do I need to prove that this is a tautology? Well, actually, no, because um, uh, the if I rewrite this implication by its valid contrapositive format, I will fall into a modus ponens case or rule, and the same proof that I did earlier will also apply to this formula here. Okay, so please allow me to skip the details of this proof because it's exactly the same as what we have done for the modus ponens argument. Let's check another argument form or another inference rule form. So it's called the hypothetical syllogism or the transitive implication. So whenever you have P implies a Q and a Q implies R, then you can conclude that P implies R. Okay. So if for rain to take place, you need clouds, and in order to clouds for the clouds to form, you need evaporation. Then clearly, okay, you can say that in order to have rain, then evaporation must have taken place earlier. Okay, otherwise you could not have rain. Okay. So it's the transitive implication effect. Okay. It doesn't mean that you have evaporation. It doesn't mean that you have rain. You just conclude another rule. So from these two rules, where the conclusion of one is the premise of the other one, you can create a new rule where the premise of the first one implies the conclusion of the second one. Okay. Um, well, actually, we can prove this one, and I think you have it in one of the equivalence rules of the tables that are given in the equivalence rules deck of slides. Okay, so you can check it, and of course, you can also prove it on your own. What else? We have the disjunctive syllogism. Whenever you have P or Q and you have not P, then necessarily you have Q. Well, it's quite easy to prove this one. This is also a different form for the, or a different reading for the modus ponens. Okay, we take it for granted without requiring you to rewrite this as an implication to apply modus ponens on it. Okay, but to prove it only once in a lifetime, let's replace P by not P. Okay, so you know that not P is equivalent to P. So without any problem, let me do it on another line. So I can rewrite P or Q as not P, okay, or Q, okay, without any problem. They have exactly the same meaning. But not P or Q is not A or B, okay, and not A or B is equal to A implies B. Okay, so if I put not P here and the Q there, okay, I will get something like this. I will get not P implies a Q. So yeah, P or Q is equivalent to not P implies a Q. So now you can apply the modus ponens on these two, okay? You have something that implies something else, and you have that premise, then clearly the conclusion must hold, okay? So briefly, whenever you have P or Q and you have not P, then necessarily you must have Q, okay? So an example on this would also be the rain and the cloud example. So usually it's not rain, okay? or clouds. Okay, so pick up whatever you want. If you have not clouds, then necessarily you have to conclude not rain. Okay, but if you add to this one rain, okay, then necessarily you have to conclude the other part, which is clouds. Okay, so it's very awful. Clouds. Okay, so yep, and this all these formats are just different readings of and different formats, syntactical flavors, different flavors of the Modus Ponens rule. Okay, let's check these two rules, the addition and the simplification. Well, they seem a little bit weird at the beginning, but you will understand their utility with a few examples. So the first one comes from the fact that P implies P or Q is a tautology. Okay, if you have P true, then you have P or anything else as true. One question that comes to the mind of the students when they first see this rule is, why would we actually add something that we don't know anything about it? Why would we add it to a fact so that it doesn't change, let's say, the truth of that fact, and it makes it a little bit more ambiguous, okay? Because we had a neat fact. Today, P is true, okay? Why would we introduce a new fact that we know nothing about it, okay? Just as if it was a noise that we are introducing in our formulas. Well, actually, the reason is quite technical. So first of all, you have to be convinced that this is a tautology. And you can easily check this with the truth table. Whenever P is true, then P or anything else is true, okay? Whenever P is true, P or anything else is true. This is clear because true or anything else is true, okay? So you can get it from the equivalence rule. So first of all, you should agree that this is a sound step. And now I can show you when this could be useful. So suppose you have this formula. So S implies P or Q. Sorry, S implies P and Q. Okay, and you have not P. Okay, so a question could be, can we conclude S, or actually not S from this? Okay. Well, if you look at your formulas, if you think about Modus Ponens, Modus Tollens, etc., you don't see maybe a logical correlation between the two formulas, especially that you don't know anything about Q. But watch it. If you start from not P and you use the addition inference rule, well, you can actually from not P you can conclude anything you add with an or to the not P. For instance, not Q. Why am I adding not Q here? Because I know that not P or not Q is the negation of this one. And I know that the negation of this one would give me not S if I'm using the contrapositive of it, or if I'm directly using the modus tollens. So do you see? So now I can just rewrite this one using De Morgan's law as not P and Q. Okay, and now I have not P and Q, and I have S implies P and Q. So from this, I can confidently conclude not S using modus, using modus tollens. Okay, I could also rewrite this one in its contrapositive form, not P and not Q, not P and Q, implies not S, okay? And then apply the, given not P and Q, I can apply the Modus Ponens rule to conclude not S, okay? So again, the Modus Tollens spares us the burden of rewriting the implications as in their contrapositive format. We can right away apply the Modus Tollens rule, okay, without going through the contrapositive. So do you see the beauty of the addition? So yeah, so maybe currently you're afraid of knowing when this would be useful to you, and you're afraid that you won't notice it, etc., because the format here was completely different from the format of this formula. But believe me, while practicing on the exercises, you will start noticing those patterns, okay? So again, what I did, I started from not P, I added not Q to it, I applied de Morgan's law, and now I have the premise of the contrapositive of this one, or simply the negation of the conclusion, so that I can apply modus tollens and get to not S, okay, which was required in the first place. Good. So just pause the video, think about it, try to do it by hand yourself, convince yourself of the utility of this inference rule, and before resuming with the next ones. Well, the next one actually called simplification. It's somehow the inverse of this process. Sometimes you have very rich information. You have a confidence about both P and the Q, but in its original format, P and the Q is not useful to you. What is useful to you is only Q, actually, you see. Okay, so yeah, so imagine the same example of the previous slide. So if S implies a P and Q, okay, and what you had in hand is not P and R, okay. Well, I think if you want to conclude not S, you will find yourself in a big trouble, because from these two formulas, you don't see the correlation. So here you have a burden with R, you don't know how to get rid of it. And here you have Q, you don't know how to introduce it. So it's exactly for these reasons that we have the simplification rule and then the addition rule. Okay, so the addition rule, it allows you to let certain symbols appear in your formulas, and the simplification allows you to get rid of extra pieces of information or data or facts that you have in hand and that are not useful to you to proving your formula. So if we call this premise number 1 and premise number 2, and here we have the conclusion C, okay? Let me show you how can I go from these premises to the conclusion C. So I will start with P2, okay? So I can say that, so usually I write the rules to the right hand side. I can say that from P2 and the simplification rule that we have on this slide, I can conclude not P. Of course, I could conclude also R alone, but R alone is not interesting for me, okay? So now, given not P and the, okay, so let's call this one an intermediate conclusion C1. So now given C1 and the addition rule, I can conclude that not P or not Q. So you can add really anything here. We could also add a Q, by the way, but it's not helpful to get to this format here. So now using, let's call it the conclusion C2. So now using C2 and De Morgan's law. So any valid equivalence rule can be used as a conclusion, as an inference step, okay? So I can now conclude that I have not P and Q. I'm sorry. So not P and Q. So this is my third conclusion. And now, given this third conclusion, given the premise number 1, and given the modus tollens, so do you see, you don't need to write everything in clear. We cannot confuse mod toll with any other rule. So you can just abbreviate it in this way. But it's really important to show us the steps when you do this entailment by hand, okay? So given these two, now I can confidently conclude that not S, okay? Because I have not the conclusion, so necessarily I should have not the premise. And now I reach my final conclusion C. Okay, so do you see? Simplification and addition, they are really useful to manipulate your formulas in order to get rid of certain details unuseful details or to add certain terms so that you can show up or let appear certain forms that are useful for you to make your proof. Of course, if you don't want to use the simplifications and additions, you could analyze this formula alone and rewrite it using equivalence rules and do this one too. And I'm quite sure that at the end you reach the same result. Okay, they are there, the addition and simplification, just to make your life easier and to help you go to the conclusion in the fastest way. The two other rules that we still have to go, they are quite straightforward. So the conjunction, it's the inverse of somehow of the simplification rule. Whenever you have two different facts, P and Q, well, then you can combine them in this way. So you need to have P true and Q true assumed to be true. And then in this case, you can say that P and Q are true. Okay. You can imagine, for the same reason that I mentioned earlier on the simplification and addition rules, sometimes you need to do this just to get your formulas in the right shape before applying the other rules. The last one is the resolution rule. It says that not P or R and P or Q is equivalent to Q or R. Okay, so maybe it's shocking at first, but yeah, like I have two words to say about it. So the first one is how can you detect that you have such a pattern, and how you can apply it. So how to apply it. So whenever you have not something, okay, so we have not P or something else, and P or something else, no matter what you have here. So R and Q, they could be any compound formula, okay? So you just, as if you were simplifying P and not P, and then you just get directly to Q or R, okay? So this is the technical aspect. But now, what about the meaning of this rule, and why is it valid? Well, actually, it quite relates to the double implication, or actually the transitive implications that we call hypothetical syllogism. Okay, I mean this one sorry. So the one that we have learned earlier. Yeah. The hypothetical syllogism, this one, or the transitive implication. So P implies a Q and a Q implies R, means that P necessarily implies R. Okay, so the disjunctive resolution, okay, so the resolution rule is just another way of seeing the transitive implications, or what we call the hypothetical syllogism. Okay, so let me show it to you. So actually, when you have not P or R, okay, when you have not P or R, you can see it as P implies R, okay? But P or Q can be seen as not Q or P. Do you agree? So that we can see it as not Q implies P. Okay, so we can see it as not Q, I'm sorry, implies P. Not Q implies P. And now you can apply the earlier rule on the transitive implication. So since you have not Q implies P and P implies R, then you can confidently conclude from it that not Q implies R. Okay? But not Q implies R is nothing but not Q or R, which is actually Q or R. Okay? So this is why we can conclude the Q or R from these two premises. Okay? So good. Let's consider an example. They are asking us whether the following argument is valid. The argument says, if this is true, then this is true. So we have a rule that says if this is true, then this must be true. And we have another fact saying that square root of 2 is strictly greater than 3 over 2. And the argument is having this conclusion, that 2 is greater than 9/4. Okay? Well, actually, this fact can be represented with a proposition called P. This one, you can call it Q. And yeah, if you have P, then necessarily Q must be true, okay? So you can see that these two are the same, okay? The square root of 2 is squared is equal to 2, and 3/2 squared is equal to 9/4, okay? So they are asking us if when P implies a Q and we have P true, whether we can conclude Q or not. Well, actually, the argument is valid. The argument is valid, no problem. But is the conclusion effectively true? So is Q really true? Well, actually, I don't think so, because if you look at P, stating that square root of 2 is greater than 3/2. We know that square root of 2 is actually a 1.4, okay, which is not strictly greater than 1.5, okay? So clearly, since the one of the premises is not true, then the conclusion cannot be true, okay? So again, if you are making an investigation, you know that on a crime scene, okay, implies suspects, okay, and in case you have an evidence or a testimonial by someone saying that that person was on the crime scene, then you should necessarily suspect that person. Okay, it's the conclusion here is really okay, and the police man will absolutely arrest that person. Okay, but of course the judge will try to make sure that this claim is true in the first place. Okay, to be able to finally make the final judgment about the suspect. Okay, so you need to check this, because this is something that was said by someone. Okay, we don't have maybe videotape or camera showing physically that that person was really there at the same time, etc., etc. Okay, so until you make sure of this premise, you cannot be sure of the conclusion. But just logically, propositional logic and the human logic that we know and that we formalize with these operators allow us actually to confidently say that this argument is valid. The argument is good, is valid. Okay, now to be sure that the conclusion is true, you need to check all your premises. And this is what the investigators usually do, or the testers of systems, etc., etc. Building valid arguments using rules of inference. Maybe I already showed this to you in earlier slides. So usually to build a valid argument, we use a sequence of statements where each statement is either a premise or follows from previous statements by rules of inference. So I did this exactly when I explained simplification and addition to you. And in this case, the last statement is called a conclusion. So a valid argument takes the following form: S1, S2, etc. up to Sn, and then finally we have a conclusion C. And this is equivalent to the fact that actually S1 and S2 and etc. And Sn, they imply C is actually a tautology. Okay, an example here is when you have P and P implies Q, then you can show that Q is a conclusion. To do so, as I told you, we can start from this premise. We can also use the conjunction, relaxing inference rule to conclude P from P and P implies Q. And we can also apply it to get P implies a Q alone. And now we are ready to apply the modus ponens syntactically and just to conclude Q. Okay. Another example where we are also translating at the same time from English to logic. So they are saying that when it's not sunny, or actually, sorry, today or this afternoon, it's not sunny, so it's not sunny, and it's colder than yesterday. Okay, we will go swimming only if it's sunny. So usually when you have P only if Q, okay? So you write it as P implies Q, okay? So we will go swimming only if it is sunny. So swimming implies sunny. If we do not go swimming, then we will take a canoe trip. So this is a typical if P then Q. So we shall write it as so. So not swimming implies canoe trip. Okay. If we take a canoe trip, then we will be home by sunset. Okay, it's also yet another if then. So it's an implication. Canoe trip implies sunset. Okay, or SS just to show SS in it. Okay, and now I think they have a question in their head. Will we be home by sunset? So do we have SS finally? Can we conclude SS? Okay, so one trick that you can apply is what we call backward reasoning. Okay, so you can start from your conclusion. Okay, so you want to have SS, but you know that to have it, you need to have canoe true. But to have canoe true, you need to have not SW. Okay, not swimming. Well, to have not swimming, this is equivalent to not sun implies not swimming, okay? So to have not swimming, you need this premise, which is not sunny. And this exists here in this conjunction, okay? So this is why now you can do the reverse order. You would say, let's call them P1, premise number 1, premise number 2, premise number 3, and premise number 4, okay? And for this one, we are not going to use the contrapositive. We're going to use Modus Ponens right away. So let's see how we can do it. So from P1 plus the rule for the relaxing the conjunction, we can conclude not S. From this new conclusion, so let's call it C1. From C1 and the Modus Ponens, we can conclude not swimming. Okay, so this is conclusion number 2. And now from not swimming and Modus Ponens. Okay, and also yeah, so I forgot on this line to mention that I need C1, and so on this line to go from here to there, I need not the conclusion number 1, which is not S, and I need the premise number 2, okay, which is SW implies S, and I need Modus Ponens, okay, guys? So on the third line, after having not SW as a conclusion, intermediate conclusion, I can add to it the premise number 3 and apply the normal Modus Ponens, direct Modus Ponens, okay, just to go to canoe. So now I have canoe trip necessarily, and then from this conclusion number 3, plus the premise number 4, okay, and plus normal Modus Ponens rule, I can go to sunset, okay, and yeah, we will be home by sunset according to the premises and the logical inference rules, okay. So you can check the details on your own. They are using in the slides slightly different symbols, and but it's the same essence. So next time we will check the 4 rules, 4 inference rules that correspond to predicate logic. So stay tuned, and we are going to discuss all these details on Thursday, so that you can do the formative quiz and the assignment as required on time by the weekend. Thank you for your time, and see you soon.